right, good morning, everyone. So if you see me constantly turning my head and talking in this direction, it's because my son is here. So hopefully it doesn't make too much noise. We'll kind of see how that works. So good. So let me share my screen here. So go back to here, share screen. All right, so we'll start off some announcements slash reminders. So don't forget, our next exam is not this Friday, but the following Friday. Seems like we just had our other one yesterday. So yeah, every 3 weeks, basically. So exam 3 will be 1 week from this Friday. Exam 3 examples I just posted on Blackboard a little while ago. So those are there. So those are on there now on Blackboard. Ahmed. Shush. And then Wednesday, we'll also do a virtual learning day. So we're going to be on Zoom today and tomorrow, and then next Wednesday. Okay. So just to warn you about that now. So good. So let's remind you what we're talking about on Monday. So on Monday, we started looking at the microscopic version of Ohm's Law, basically. So here I have a wire again. We're going to supply a potential difference across this guy. So here's our potential difference. And then that's going to establish an electric field. So that electric field then is going to point in, say, this direction. And then that's going to cause the charge carriers to then move on the inside. So again, these guys are going to move. So this is charge Q, and it's going to move on average with the drift velocity of VD. So what we found last time was that the current then is equal to the charge times N, where again, N is equal to capital N divided by the volume. So this is what's called the number density. So this is the number of charge carriers per unit volume times the cross-sectional area. So that's the cross-sectional area, in this case of, say, my wire, times the drift velocity, which means that the current is essentially just the average velocity at which the charged particles move across the wire, or whatever the circuit element is. And then from there, we can come up with the current density, which again is the current per unit area, which is then the charge of the charge carriers, times then the number density, times then the drift velocity. And again, this one is a vector, where this one is simply a scalar quantity. So let's do some examples of this. So let's look at our first example. Once I find it, here we go. So the first example says, let's go over a little bit. So this says, near Earth, the density of protons in a solar wind, which is a stream of particles from the sun, is about 8.7 protons per centimeter cubed. Pardon me, and their speed is about 470 kilometers per second. So the first thing we want to know is, what is the current density of these protons? And then for part B, we want to know, if the magnetic field of the Earth did not exist, which if it didn't, we'd all be dead, what is the total current the Earth would receive? And we'll talk about what all this stuff actually means here in a second. So good. So let's look at this example. So this says that we have the Earth. So here's the Earth. Good. Here's my Earth.
Daddy, I went into movie games and movie videos, but now they're just pictures.
I see. Okay. Can you put your headphones back on? Okay, thanks. So we have the sun, and then the sun is going to send out charged particles. So anybody know what actually solar winds are? Really? So in the sun, you get these magnetic fields, and the magnetic field can actually explode out from the sun, creating these things which are called promenades. So basically it explodes out through the sun, comes around, and then goes back into the sun. And if these promenades get too big, what'll happen is actually they break. And when they break, they send a whole bunch of charged particles basically flying in all different directions, which on average will be towards the Earth. So it's basically just a whole bunch of charged particles. So here we're told that the number density is 8.7 per centimeter cubed, and that these guys are moving with a velocity, which we're going to call the drift velocity, of 470 kilometers per second. Is that right? Yeah, per second. Good. Now, the point of the Earth's magnetic field is that the Earth has a magnetic field. which basically does something similar to this. And what the solar winds do is they actually get caught up in the Earth's magnetic field, causing this portion of the Earth's magnetic field to actually get dragged way out in this direction. But the magnetic field of the Earth actually shields the Earth from all of these charged particles, which means that if we didn't have the magnetic field, we'd be constantly bombarded with these charged particles, which means we'd have a current going across the surface of the Earth. And we'll talk about the size of the current here in a second, but basically the surface of the Earth would constantly be scorched and there'd be no life on Earth because we'd all be dead, basically. So that's solar winds. So good. So part A, we're looking for then the current density. So what's the magnitude of the current density? Good. Well, we now know that current density is equal to the charge of the charge carrier times the number density times the drift velocity. Right? So for us, we're talking about protons. So the charge of a proton is simply the fundamental charge times the number density times that drift velocity again. So this is going to be 1.602 times 10 to the minus 19 coulombs times the charge density, which we'd have to put into meters cubed, but I'm just going to add a centimeters cubed for now, times the drift velocity, which we'd also have to put into meters. But again, I'm just going to put this into kilometers. So after I do my conversions, what I find in this case is that this works out to be about 6.54 times 10 to the minus 7th amps per meter squared. So this is my current density. Part B then wants to know, okay, so what then would be the current from this current density that would be passing past the Earth? So basically I would have a current running through the Earth, and I want to know what is that current that's basically running through the Earth. Okay. So let's look at part B.
Daddy?
Yes?
There's a really big island and it's in, that's strange, North America.
But North America is a very big island. Yes, it's actually a very huge island. So we now know currents is equal to current density times the area, right? So this is going to be equal to our current density, which was QNVD times the area. Now, what we need to know now in this case is what area are we caring about? So again, we're looking at the Earth, and the charged particles are moving in this direction. So this is our drift velocity, and this is our current density. So this area here is either going to be the surface area of the Earth, which we know in this case, the surface area, thanks to Gauss's law, is either going to be 4 pi times the radius of the Earth squared, or it's going to be the cross-sectional area, which in this case, the cross-sectional area is that of a circle, which is going to be pi times the radius of the Earth squared. So the question is, which one of these areas is it? Do we care about the surface area, or do we care about the cross-sectional area? So which area do you think we care about? So as the charged particles are moving towards the Earth, is it effectively going to see it as a sphere, or is it going to see it as a circle? So that's the question. So what do you think? Is it going to see it as a surface area, or is it going to send it or see it as a... Good, Dylan. That's right. Just a circle. So in this case, all we care about then is the cross-sectional area. That's right. So this is then going to be simply Q times N times VD times pi times the radius of the Earth squared. So after we look up the radius of the Earth, we find then is that this works out to be about 8.34 times 10 to the 7th amps. Okay. That's a huge amount of amps. So out of curiosity, anybody know how many amps it takes to kill a person?
Is it like half?
You cut off quickly, Dylan, or Derek. What was that?
Is it like half?
It's about 100 is basically. So about 100 amps would actually kill a person. So this is what, 10 to the 5th times greater than 100 amps, right? So basically nothing on Earth would actually be able to live thanks to this amount of current from these solar winds. So we'd all basically be scorched and dead and all kinds of fun stuff. So. All right, let's do another example. So the next example says, example number 4, that we have a copper wire, which has a diameter of 3.2 millimeters and carries a current of 5 amps. So we want to determine the current density in the wire, the drift velocity of the free electrons moving within inside of the wire, and then part C finally estimates the RMS speed of the electrons, assuming that they behave like an ideal gas at 20 degrees Celsius. And we're going to assume that there's 1 electron per copper atom is free to move. Okay, so let's talk about this one. So, okay, so here is my wire. So let's say here's my wire. This thing has a diameter, okay, D, where we're told that D is equal to 3.2 millimeters. So this is my diameter. And this thing is going to carry a current. So let's say our current is moving in this direction, where that current then is 5 amps. So good. So part A, we want to know from here, what is that current density? So what's the magnitude of that current density? Well, we now know 2 things. So we know that current density is either going to be the charge of the charge carrier times the number density times the drift velocity. But to use this, we need to know what N is, which we can look up because we know it's copper. So that's not a big deal. We need to know what Q is, which we also know because it's an electron, which is moving. So we know the fundamental charge. But we need to know the drift velocity. But then part B is saying, okay, well, what's the drift velocity? So we don't actually know that quantity, right? But the other thing we know is that current density is simply equal to the current divided by the cross-sectional area. So in this case, we know the current, we know the cross-sectional area since we know the diameter. So here, the cross-sectional area is just going to be what, pi times the diameter squared divided by 4. So then we can solve for the current density. So this says then the current density is going to be 4 times the current divided by pi times the diameter squared. Playing our numbers, we get in this case then is this works out to be about 6.2 times 10 to the 5th amps per meter squared. So this is our current density. Part B then says, what is the drift velocity? So what's the drift velocity? Well, using what we originally wrote up here for the current density, this then says that what? We know the current density is equal to the charge times the number density divided by the drift velocity, which means the drift velocity then is equal to the current density divided by the charge, which is our fundamental charge, times the number density. So from here, we just have to look up the number density. So the number density for copper is equal to 8.5 times 10 to the 28th electrons per meter cubed. So this is our number density for copper. Plug all that in, we find in this case then is that the drift velocity works out to be about 0.05 millimeters per second. So this is our drift velocity. So what that means is that the electrons moving inside of this wire here at 5 amps are moving at a rate of 0.05 millimeters per second. That is ridiculously slow. I think if they were racing a snail would win. Everybody's okay? Good. Now, to make a better point out of this, part C then wants us to look at the RMS velocity of the electrons moving inside of the wire if we measure it or assume it's an ideal gas. So remember that the RMS velocity from last semester is equal to the square root of 3 times Boltzmann's constant times the temperature in Kelvin divided by the mass. Okay. So here our temperature was equal to 20 degrees Celsius, which is equal to 293 Kelvin. The mass is the mass of a copper atom. KB, I don't remember off the top of my head what that actually is. But anyways, if we look it up and we plug in our numbers, we find is that the RMS velocity inside turns out to be 1.2 times 10 to the 5th meters per second. Okay.
Daddy,
Yes, my son.
is it okay if I take pictures of you? But
While I teach? I guess if you want to.
no, I already took pictures.
Oh, okay.
But
Are you going to post them all over the internet?
Well,
I hope not.
Daddy,
Uh-huh.
I'm trying to get onto a video.
Well, you'll have to figure that out because I'm busy right now. We'll put it on later. Okay. Okay, good. So let's go back. Let's compare now these two numbers. So we had the drift velocity was 0.05 millimeters per second. And now what we're saying is that the RMS velocity, though, inside of the wire of the particles moving in different random directions is 1.2 times 10 to the 5th meters per second, which is the same thing as 1.2 times 10 to the 8th millimeters per second. So it's a drastic difference between the two. So this actually kind of gives us a good idea of what the particles are actually doing on the inside. So if I look at my wire, so let's say here's the wire, let's draw a big old cross-sectional area for the wire. So what's really happening inside the wire is that the electrons are basically moving around in all kinds of different directions, as if they're a cloud of electrons basically moving in different directions. With an RMS velocity, on average, this thing is kind of moving around. So I have all of these electrons basically zipping around in all kinds of different directions. But then when I apply the potential difference across the wire, so here's my potential difference, setting up the electric field, what that does is it causes this chunk of electrons randomly moving around, causing it to drift in the direction of the electric field at a very slow rate. So again, all these electrons are flying around on the inside, but basically these electrons moving around with a, you got your feet? Very nice. So all these electrons moving in all kinds of different directions are then slowly drifting down the wire in the direction then of the electric field. Right? So if my electric field is pointing in this direction, then I have a slow drift velocity causing this chunk to slowly move down at a ridiculously slow rate, while the electrons themselves are flying around inside of this wire at a very high rate. Right? So this is actually what's happening inside of the wire. So we can actually imagine that the electrons moving inside the wire are a gas, and that gas is slowly propagating downward as all of the electrons are zipping around in different directions. So I have a slow migration basically heading down the wire. So to put that in a little more context, I have a light switch over here, I have a light behind me, and let's say the distance between the light switch and the light is 1 meter. So what this says, at this rate, if I turn on this light switch, it takes exactly 5 hours for one electron to move from the light switch into this light. So 5 hours for this electron to move that distance. But as soon as I turn on that light switch, this light turns on right away. So why is that? So if it takes the electron 5 hours to move from the light switch into this light bulb, then why does it turn on when I turn this thing on? So as soon as I flick that light switch, the light turns on. So where's the discrepancy in this case? So what do you think?
Is it the electrons are like pushing like the electrons that are in the wire, like that are?
That's right. There's not just one electron. Exactly. That's the answer. So even though it takes that one electron by the light switch 5 hours to move all the way down to this light bulb, but there's also electrons everywhere within inside of the wire. So that's right. So as soon as you flick on that light switch, those electrons start pushing that first one in. So as soon as you switch that switch, the light bulbs, which are inside of the wire, basically going into the lights, will fall in immediately, which actually causes the light to move on. Exactly. So again, we have a very slow propagation of these guys down, but again, our wire is fully saturated with charged particles at all times. That's right. Good. So the next thing we want to talk about is what's the relationship then between the electric field and the current density? So what's the relationship between these? Okay, so what is the relationships between these guys? So to answer this question, we're going to start off with Ohm's Law. So remember, Ohm's Law says that the change in potential that we supply across some sort of resistor is equal to the current times the resistance. So what do we know? We know current is equal to current density divided by cross-sectional area. We know the resistance is equal to, oops, sorry, that was wrong. It's times area. What am I doing? There we go. So current density times area. There you go. Resistance is equal to resistivity times the length divided by the cross-sectional area. And we also know that the change of potential is then equal to the electric field times the distance between the two. Or in this case, the distance is simply equal to the length. So let me rewrite that as the length. There we go. So let's use all these things into here. So what this says then is that the electric field times the length then is equal to the current density times the area times the resistivity times the length divided by the area. So here, this area is going to cancel this area. This length is going to cancel this length. So from here, this says that the electric field then is equal to the resistivity times the current density. Or, as we talked about on Monday, we can also rewrite the resistivity as 1 over the conductivity. And then we can write this as the current density then is equal to the conductivity times the electric field. So this is the relationship then between the electric field and the current density. So all this thing says is that the current density then points exactly in the same direction as the electric field because the conductivity is always a positive quantity. This thing is never going to be negative. So meaning if my electric field through the wire points in this direction, then my current density has to be in the same direction. Okay. All right. So this thing is what's known as the microscopic version of Ohm's law. So this is the microscopic version of Ohm's law. So let's use this and let's do an example. So let's look at example number 5. Example 5 says when we have 115 volts is applied across a wire that is 10 meters long and has a radius of 0.3 millimeters. The magnitude of the current density is 1.4 times 10 to the 4th amps per meter squared. We want to know then what is the resistivity inside of the wire. Good. So let's talk about this. Where am I? Here I am. Would you stop doing it? I hate it when it's whoops.
4.
What did I do? What did I do? Oh no, what did I do? All right. Okay, how do we get back here? There we go. Okay. Whew, that was scary. Okay. So anyways, so we're told that here's our wire. Good. So our wire is, what was it, 10 meters long? Yeah, 10 meters. So this has a length of 10 meters. It has a potential difference applied across it. That potential difference is then 115 volts. And also has a diameter, which was equal to 0.3 millimeters. Good. Amen. Good. So we want to know what is the resistivity inside of the wire. Good. So what is my resistivity inside the wire? Good. Well, now what do we know? So we know that the microscopic version of Ohm's law says that the electric field is equal to the resistivity times the current density. Or magnitude-wise, it says the electric field then is equal to the resistivity times the magnitude of the current density. Bless you. It's okay. So now what? So we know the electric field again is going to be equal to the potential difference divided by the length of the wire, and that's equal to what? The resistivity times the current divided by the area. You okay? Go blow your nose. You got snot on your face. Go blow your nose. Go blow your nose. Go blow your nose. Good. So anyways, where was I? Good. So it says that the resistivity then is going to be equal to what? The volts divided by the length, good, times then the cross-sectional area divided by the current. Good. Right. So plug in our numbers, we find in this case is this works out to be 8.2 times 10 to the minus 4th ohm meters. Good. So this is our resistivity. Good. Okay. Hopefully, sorry, too many distractions. We'll do our best. Okay. So good. One more topic to talk about in this chapter, and that's electrical power. So let's talk about electrical power. Good. So the first power we're going to talk about is what we're going to call power delivered. Good. So let's talk about power delivered. So remember power, let's talk about power. So remember power is equal to the rate of change of work with respect to time. So this is power by definition. So let's say what we have is some sort of electrical object. So here's my electrical object. I'm going to randomly draw this. This thing has some sort of potential. So this thing has a potential difference of, let's just call this V. And what I want to do is move a charge of charge dq across this electrical object. So what we want to know then is how much work is required to move this amount of charge dq across this electrical object, those electrical elements. So the differential amount of work dw then is going to be, so you remember work is equal to q times delta v. So this is just going to be then V times then dq. Okay, so this is the amount of work it takes to move this thing across this particular electrical object. Now, if it takes an amount of time of, say, dt to move it across this thing, so the amount of time is equal to dt, then the power delivered is then equal to dw dt, which is then simply equal to V times dq dt. But what's dq dt? What's dq dt by definition? So where did we start this chapter off?
Is it the derivative of charge?
Yep, derivative of the charge with respect to time. And what do we call that by definition?
Is it current?
It's current. Good. So remembering that the current is simply dq dt, then that says the power delivered then is equal to the potential difference times the current. So this is power delivered. So what this thing says then is for this thing to have a potential difference, meaning I have to apply a battery to it, then the power delivered by the battery to move this thing across this electrical element is simply equal to the potential difference across this element times the current. Now, conservation of energy tells us, though, if this is the power which is delivered, then I have to also have a power lost by this electrical element to abide by conservation of energy. So whatever I supply to it, I also have to simultaneously lose it. So conservation of energy tells us that the power lost must be equal then to the power delivered, which means that the power lost, supplying power to this electrical element, then is equal to the potential times then the current. Now, if this electrical element is equal to a resistor, then this also has to abide by Ohm's law. So Ohm's law again says that the potential is equal to the current times the resistance. So I can also write the power loss as then being the current times the resistance times the current, which is then equal to the current squared times the resistance. Or I can rewrite the resistance as the potential divided by the current, and then rewrite this then as what? Let's do it this way. Actually, let's rewrite I. So it says I then is equal to V over R. So this is going to be V times V over R, which is then the same thing as V squared over R. So any one of these things is equivalent. So the power lost through any type of electrical object is then either equal to the potential times the current through that object, or if I'm dealing with a resistor, it's the current squared times the resistance, or the potential across it squared divided by the resistance. Any one of these is equivalent. So this one is good for any type of electrical element. These two are only good for resistors. Okay. So good. So this is the power law. So again, the power which is delivered by the battery to the electrical circuit to move a single charge of dq across this electrical element, which has a potential difference of V, is then equal to, again, by conservation of energy, the power lost by that electrical equipment to move it then across that object. Okay. So let's do a couple examples. So let's look at the first example. So first one says, where are we? Number 6. There is much variability into a lightning bolt, but a typical event can transfer about 10 to the 9th joules of energy across a potential difference of 5 times 10 to the 7th volts during a time frame of about 0.2 seconds. So let's draw what's happening here. So basically what happens is here's the Earth. Here are the clouds. And then what you get is between the Earth and the ground, you get a potential difference of V, which is equal to about 5 times 10 to the 7th volts. Okay. Then lightning strikes. Here's my lightning. Inside of that lightning, there is an energy where that, let's see, that energy, let's call that U, is equal to about 1 times 10 to the 9th joules. Okay. And this happens in a time frame of delta t, which is about 0.2 seconds. Okay. So part A, what we want to know then is what is the amount of charge contained inside the light bulb? So, or not light bulb, sorry, lightning. So how much charge is inside of the lightning? Part B, we then want to know what is the current carried from the ground to the clouds. And then finally, part C, what is the power? Okay. So let's talk about this a little bit more. So what happens is the clouds get positively charged. The ground is basically an effective, reservoir of negative charges. So the Earth becomes negatively charged. So I have a positive plate here. I have a negative plate here. This is basically a parallel plate capacitor. Right. So between the clouds and the Earth, I have a parallel plate capacitor, which ends up with a potential of 5 times 10 to the 7th volts, which then causes ionization of the air. So I have a breakdown of the potential. And when this happens, actually, lightning doesn't strike from upward to downward, it actually strikes from downward to upward. So what actually happens is the clouds strip electrons out of the Earth, and they actually move upward through the ground into the clouds to dissipate the charge inside of the clouds, causing the lightning to actually strike from the ground up instead of from the clouds down. And this is actually how lightning works. It goes down to up instead of up to down. So it actually goes backwards than what we actually think it does. So first thing we want to know is how much charge is contained inside of these guys. Right? So let's talk about the charge. So for part A, well, again, we know that the change in potential energy is equal to the charge times the change of potential. Right? This is something we learned back from the last exam. So according to this, the charge then is going to be equal to the change in potential energy divided by the change of potential. So here, change of potential energy is 1 times 10 to the 9th joules divided by the change of potential, which is 5 times 10 to the 7th volts, which in this case works out to be about 20 coulombs worth of charge. That's a huge amount of charge. Part B, we now want to know what's the current. Well, again, we know current by definition is the change in charge. So Q divided by the change in time. So this is going to be what? 20 coulombs divided by 0.2 seconds, which is 100 amps worth of current. And as we already talked about, 100 amps worth of current will stop a person's heart and kill a person. So this is why a lot of people die when they're struck by lightning. Nice. Part C, we now want to know what's the power. Well, we know power, again, by definition, is equal to the change in work with respect to time. But remember that work is equal to minus the change of potential energy. So this is also, whoops. What was I? There we go, thank you. So we can write this then as equal to the change in potential divided by the change in time. So this is then going to be equal to 1 times 10 to the 9th joules divided by 0.2 seconds. Good. So this works out to be about 5 times 10 to the 9th watts, which is equal to 5 gigawatts. So this is the amount of power which is delivered by a strike of lightning. Okay. Anybody ever seen Back to the Future, the original Back to the Future? Remember towards the end, Doc Brown kept running around saying gigawatts, gigawatts. Well, this is where this comes from, right? It's actually gigawatt, not gigawatt, but there's a tremendous amount of power delivered inside of a bolt of lightning. So good. Let's do one more example. So the last example, then we'll talk about some other things here. There you are. Last example then says, the current density magnitude in a certain circular wire is J equal to A, where A is some constant, which is 2.75 times 10 to the 10th amps per meter to the 4th, times the radius squared in a wire of radius 3 millimeters. So the potential applied to the wire end to end is 60 volts. So we want to know how much energy is converted to thermal energy in 1 hour. So good. So this is what we want to know. So let's talk about this. So good. So here, I'm told here's our wire. This thing has a radius. Let's call that little r. Actually, I don't want to call it little r. Let me call it A. Call it something different. A is equal to, what was that? 3 millimeters. So this is my radius. This is equal to radius. Across here, we're going to supply a potential difference, delta V, which is equal to 60 volts. And we're told inside of the wire, we have a current density, which is equal to A times R squared. So good. So now we want to know what is the energy which is being radiated. So first thing we need to know then is what is the power? Where again, the power is the rate of energy. So this is the change in energy with respect to time. Well, we know power is also equal to the current times the potential. So here we know the potential, that's simply equal to 60 volts. We now need to know the current. So the first thing we're going to find out is what is the current? Well, we know current is equal to the integral of the current density integrated over the differential area. Whereas we talked about last time, the differential area then is going to be 2 pi r times dr. So we're going to integrate from 0 to A of then J, which is A times R squared, times dA, which is then 2 pi R dr. So this is going to be equal to then 2 pi times A times the integral from 0 to A of R cubed dr. What's the integral of R cubed dr?
R to the 4th over 4.
Good, R to the 4th over 4. So from here, we now get the current is then equal to 2A times pi times then A to the 4th divided by 4, which is the same thing then as what? Pi times A to the 4th divided by 2. Okay, so this is our current. So this as our power then is going to be equal to what? 1/2 pi A to the 4th times the potential. But we want to know what is the energy. So we know the energy then is going to be equal to what? The integral of the differential energy, which is then equal to the integral of the power integrated over time. Now, but from here, we can see that the power has no time dependence to it at all, which means the power would come out. So we would simply integrate, in this case, the dt, which is simply the change in time. So the amount of energy which is going to be lost then is equal to the power simply by the times the change in time. So this is then equal to 1/2 pi times a to the 4th times the potential times then the change in time. Here, our change in time, since we're looking at 1 hour, that's going to be equal to 3,600 seconds. So plug in our numbers, we find in this case then is the total amount of energy which is lost is 7.5 times 6 times 10 to the 5th joules. So you're actually losing a tremendous amount of energy over this wire. So this is the energy which is lost. Okay. So good. So let's talk about something real quick. So even though we've said so far that a wire, we're usually going to look at as a wire has 0 resistance, but that's not necessarily true. So in reality, a wire also has a resistance, but it's a very small resistance. So it has a small resistance R. So having said that, what that means then is that even a wire, which is running through your house or your car or your computer or anything like that, is going to lose energy. So the power which is lost inside of the wire is simply going to be the current which is running through it squared times the resistance, or again equal to the potential squared divided by the resistance. Which means that what? If I have a pretty high current running through a wire, that wire is going to get very hot. It's going to lose a lot of energy because, again, remember that what? As the temperature increases, due to the fact that we have a kinetic energy increase. So as the atoms are coming through here, or actually the electrons are slamming into the atoms, those atoms, again, are going to vibrate faster and faster and faster. They're going to gain more and more and more amount of kinetic energy, which means the temperature is going to go up. As the temperature goes up, more power is lost, which means that these wires are going to get very hot. Now, that brings me to a question. Anybody know what the reason for a breaker box is in your house? So what's the point of putting in a circuit breaker in your house or in your car? Your car also has a circuit breaker in it, right?
So you don't burn down your house?
Exactly. That's right. So what the breaker does is for each wire that runs through your house, you have a different gauge of wire. So gauge of wire just refers to the radius of the wire. So for higher gauges, that's a smaller radius. Smaller gauges, that's a bigger radius. So what that means is the bigger the radius is, in that case, that means the bigger the cross-sectional area it is, which changes then the resistance. As the resistance changes, what will happen then is, thanks to this quantity here, as the resistance goes down, the current goes up, which means the power loss is then going to become bigger and bigger and bigger, which means that the temperature is going to get higher and higher and higher. And what eventually happen is if you run too much current through a particular gauge of wire, it'll become too hot and your house will actually start to catch on fire, or your car, or your laptop, or any of these different things. So the point of putting a circuit breaker in your house is for each wire that's connected to a certain electrical element in your house, it's gauged for a particular type of wire, which means that you don't want the current to exceed a certain amount, like 20 amps or 15 amps or 10 amps. So your circuit breaker is there to measure that amount of current running through it. So if it goes above that amount of current, it kills it. So that way your house doesn't burn down, your car doesn't burn down. It's put in there for a safety measure so you don't accidentally kill yourself, right? So that's basically what the point of the circuit breaker is. So to keep you from burning down your house and wasting all that money that you spend on your house, right? So that's it. So basically we're done with this chapter. Yay. So from here I have 3 group assignments for you guys. They're already posted on Blackboard, but let me bring them up so we can talk about them real quick. So the first one is my son making noises. So let's talk about the first one. So the first one has two different questions. What are you doing? Going. So the first one says we have a potential difference of 1.2 volts applying to a 33 millimeter length of 18 gauge copper wire, which has a diameter of 0.04 inches. So from here, you want to calculate the current running through the wire. You want to know the magnitude of the current density. So this is J, the drift velocity of the electrons inside there. So looking for N, the magnitude of the electric field, and then the rate at which thermal energy is lost. So you're looking for the power. So these are the quantities you need. This is the resistivity of a copper wire, and this is the number density for a copper wire. The second one then says we have a steady beam of alpha particles, which have a charge of twice the fundamental charge. So an alpha particle is actually just 2 protons. So it's basically helium atom missing its 2 electrons. So it's a fully ionized helium atom, traveling with a constant kinetic energy of 20 mega electron volts. This thing carries a current of 0.26 microamps. So this one says, if a beam is directed perpendicular to a flat surface, how many alpha particles strike the surface in 3 seconds? So let me kind of draw what this thing means. So if here is my beam of alpha particles, okay, so this thing is moving in this direction, which has a current, and then it's hitting a flat surface. So let's say this is hitting a wall or a table or something like that. What's going to happen then is you're going to build up a bunch of alpha particles on this area here, and it basically wants to know how many alpha particles are contained inside of here in an amount of time of 3 seconds. So I want to know the number of alpha particles in 3 seconds. Okay, this is part A. Part B then is saying, well, how many alpha particles are inside the beam of some length L? Okay, where L, in this case, let me go back to the question. The length here is 20 centimeters. So it wants to know within inside of this portion of beam, which has a length of 20 centimeters, how many electrons are in, or how many alpha particles are inside of this portion of beam. Okay, so basically both of these two questions for part A and for part B, you're just playing with the definition of current. Okay, where current, again, is equal to the change in charge divided by the change in time. Okay. So basically both of these two parts are kind of asking you for nifty ways of rewriting change in time, basically. Part C then is saying, through what potential difference is it necessary to accelerate each alpha particle from rest to bring it to an energy of 20 mega electron volts? So this is just conservation of energy from last exam. So here he's going to say the change of kinetic energy plus the charge times the change of potential energy, or just potential, is then equal to 0. Right? So this one is just asking for us to remember conservation of energy. So the change of kinetic energy plus the charge times the change of potential is equal to 0. So this is part C. So it's going back to that. The last question is this one. It's not going to be good. I know. So the last question says, we have a filament of light, which is made out of tungsten. So this is my filament. One second. Has a resistivity of 5.6 times 10 to the minus 8 ohm meters. And it's in the shape of a cylinder where the radius of the cylinder is 5 times 10 to the minus 5 meters and has a resistance of 20 ohms and a length of L. So the light bulb is connected to a battery, which this battery has 120 volts worth of potential. So first thing it wants to do to find out is what's the length of the wire? What is the magnitude of the electric field inside of the wire? The number of electrons per second that pass through the cross section. So the number of electrons per second is effectively the current divided by the charge on an electron. Okay. So that's the number of electrons per second. The power dissipated. And then finally, the last part I want you to say, if we turn on this light bulb for 30 days without ever turning it off, how much money would you have to pay the electric company? If the electric company charges you 15 cents per kilowatt hour. So if you look at the units of kilowatt hour, remember power is a watt. So kilowatt is just a kilowatt times an hour, that's an energy. So a kilowatt hour is an energy. So it's charging you 15 cents per energy. So per energy, which is basically lost. So it just wants you to figure out how much money do you have to spend to keep this tungsten light bulb on 30 days consecutively with never turning it off. So that's how much it wants you to estimate. So not too bad. So again, this is just using all the things we learned about. So Ohm's Law, all that different stuff. So everyone okay with these? Any questions on any of these? Hardest one is the second one, but again, this is just basically playing with the definition of current, using kinematics and other things to then rewrite the change in time as well as velocities and all that kind of good stuff. So not too bad. Everything's okay? Not too bad. So tomorrow we will then start the next chapter. So we're going to start looking at resistors and parallel and series, how to add those guys together. And then we'll eventually look at what happens if I have more than one battery. That'll bring us to Kirchhoff's loop rules. So basically how to do all that. And then I'll semi-teach you how to do matrices and basically row reduced echelon form. So that way you can do it on the exam using your graphing calculators, because all you have to do is use a couple buttons and that'll solve it for you. So you don't have to spend like 20 minutes doing algebra. So you just have to set up the equations, plug it into your calculator, and then it'll spit out the answer for you in like half a second. So it'll be great. And then from there, we'll talk about RC circuits. So that'll be the last thing in that chapter. So we're most of the way there. So not too much more to go. So anybody have any questions on anything? Again, sorry about all of the distractions. Not much I can really do about that at this stage. So tomorrow he will actually be with his mother for a little bit. So he won't be here directly with me, but then she has to leave for the rest of the day. So but yeah, so he won't be here to bother me during the class time, so it'll be fine. Okay. So any questions on anything?
On the second to last example, like the lightning one on part C, could you not use power is equal to voltage times the current, or is that not like possible for that example?
For the second to last one?
Yeah,
we could do that
like,
as well. Yeah.
Okay.
Yeah, since we already have the current, we already have the voltage, we get exactly the same answer anyways. So yeah. So in that case, your voltage is what, 5 times 10 to the 7th times 100 volts, which is 5 times 10 to the 9th watts. So same exact answer. Yeah. So either one, doesn't matter. Either one.
Could you go to part A of the lightning problem?
Sure. Okay, there you go.
Okay, thank you.
You're welcome. Everybody else okay? Any other questions? Okay. So I will then see everybody tomorrow for another round of virtual learning. That would be great. And for those of you who came a little bit later, if you missed it in the beginning, we will have another virtual day 1 week from today. So we're going to have 3 total. So after today, just 2 more left. So tomorrow and then next Wednesday. And then after that, we should be constantly back in face-to-face unless school shuts down for some reason. So that'd be great. Okay. All right. So have a good day, everybody. I'll see you all later. Thank you for coming. Bye.